St. Croix with the Statistics Division. I would like to welcome you today and thank you for joining us. Our speaker today is Dr. Kurt Magaj, who is co-founder and VP of Analytics at Sight Machine. Kurt first began his professional life as co-founder of Slashdot.org, which is a major technology news website, where he was working with big data before it became such a buzzword that it is today. He then went on to earn his PhD in business administration from the University of Michigan and was a professor at Michigan State University before leaving to found Sight Machine. He is lead author of Practical Computer Vision, a book on introductory machine vision. At Sight Machine, Kurt leads the data science team aggregating and analyzing computer vision and other sensor data. Today, Kurt will be presenting on the topic of using big data to evaluate computer vision systems. During the presentation today, all microphones and phones have been muted other than mine and Kurt's. So if you do have any questions or comments, which we highly encourage, please use the questions interface in the GoToMeeting control panel. And those questions will be forwarded directly to me, and I'll hold those for the end of the presentation, at which time Kurt can answer some of those for us. So without further ado, I will hand things over to you, Kurt, and thank you again for presenting with us today.
Great, thank you. And all right, let me share my screen here and get my slides running. All right. And hopefully you all can see my slides. Thank you once again, and good afternoon to everyone. I'm going to talk a little bit today about using big data to evaluate computer vision systems. Without spending too much time on introduction, let's go ahead and sort of dive into the goals of this presentation. I've thought about the goals from several different perspectives. One is actually sort of for a quality audience in particular, and the whole idea of big data is getting a lot of hype lately. In fact, to be honest, I don't even like the term anymore. It makes me feel a little nauseous to hear it too, but it's been sort of a term that we all hear floating around a lot these days. But one of the problems is a lot of the stuff around big data is in generalities and terms that really aren't very practical in a manufacturing context. So you might hear people talking about, oh, it's this many exabytes of data to catalog all electronic medical records in the world, or something like that. Or a lot of these applications, which most of us are not trying to catalog all of the electronic medical records on the planet. And so trying to take this from a abstract concept and make it a little bit more practical in terms of how you can actually use it. There's also a sort of technical goal just to talk about how we at Sight Machine have been tackling some problems and specifically applying big data, both in terms of collecting lots and lots of data and then using that to solve tough problems. And I'd like to really focus on sort of the process and approach that we use. So this will be sort of a high-level discussion. We aren't going to get into specific algorithms or anything like that, but hopefully give you some understanding about the challenges that we face as we try to tackle applications like this. And then kind of down at a sort of data and stats goal, like I said before, we really aren't going to get into a lot of discussion about algorithms and machine learning and all that sort of stuff, but we do want to talk a little bit about how you go about that data collection, some of the aggregations and the manipulations that we had to do in order to make this all work. So without further ado then, let's kind of dive into this a little bit. And my guess is that pretty much anybody who signed up for this webinar already has a bit of an idea of what big data is. But just to make sure that we're on the same page, I'd like to take just a couple minutes to talk about sort of the definition. So you may have already run into the 3 V's: volume, velocity, and variety. And we'll just kind of briefly unpack what that means, because sometimes there is actually even a little confusion around these ideas. So for example, volume. That could actually mean, 15 exabytes of data or something crazy where you're talking about lots and lots and lots of data. But there is also a slightly more subtle point about the volume, which is really that it's all of the data, not just lots and lots of data. So perhaps you have a process where you aren't, spitting out, exabytes of data or something crazy like that, but the philosophy here behind big data is more shifting from sort of we take samples to trying to collect all of the data that's being produced. Now, of course, that's not always practical. There are many environments where you are stuck taking samples. So, for example, destructive testing. Obviously, you're not going to destructively test every part, but nonetheless, you have this sort of underlying current or this underlying concept that you want to collect as much data as possible. The second major idea is then the velocity. So you're collecting all this data and you want to analyze it in real time. And so you're going to be taking data on a constant stream coming in, processing that data, and then spitting the results out as fast as possible. And it is really important to emphasize it's on both the incoming and the outgoing side. So you're having a steady stream that comes in, but it doesn't really count as high velocity data if you then do, say, batch processing and you don't get the results from that data for 24 or 48 hours afterwards. So velocity means lots of data coming in and lots of results coming back out. And then finally, you've got sort of this idea of variety. Many people may have heard of this idea of unstructured data. We're not going to get into some of the craziness of what that means at a technical level, but what that fundamentally means is you aren't necessarily working with highly defined data sets. You have much sort of looser information like images or text data sources or things like that, where you can't just say here's column X, column Y, and column Z. You're actually dealing with many, many different sources of data that you're trying to aggregate together in near real time. So hopefully some of that is familiar to most people who are on the call. Big data is actually a great opportunity for vision in particular. So images are a really, really rich data source. Even if you think about how you as a person sort of sense the world around you, most of the way that you sort of think about what's happening around you is something around visual data. So it's a very, very rich data source. And to kind of think about what's going on there and why it can be so rich, you can think of this image as a bunch of features that you're seeing at any given time. So let's make that particularly to a manufacturing context. If you, say, have cameras on your manufacturing line doing automatic inspection, and you may be detecting certain features like the width of the product or the color, or is there a scratch on the surface or things like that. So what you're doing is taking this sort of matrix of pixels with different colors on each pixel, and you're trying to find features on that. And what's kind of neat about this as a big data source is you can do that initial feature analysis, and then you go and you store the image, and maybe a little bit later you may have some other type of analysis that you want to perform on those same images. So maybe you had a camera where you were just looking for something as basic as, what color is the object that's passing under here. But then you have this idea that, hey, you know what? I might be able to go back and look at sources of, scratches on a product. And so I'm going to go back to my database of images, and I'm going to write a new algorithm that's going to research all of those and find scratches on the product. So it's this great data source where even once you've done a first pass of analysis on it, if you're holding on to those images, you can go back and sort of mine it for more and more and more features, even if you didn't think about it the first time you did the analysis. So it's a really rich data source for mining information. It's also, though, important to have lots of data to train a computer vision algorithm. And if you think about what goes into the human vision process, you can start to get an idea of the complexity of doing computer vision. So, for example, as a human, you aren't really just looking at a picture all the time. So, for example, you've got two eyes. So you're doing sort of what's often called the parallel or parallax effect, where you have two slightly different images from slightly different locations, and you're using that to provide information about the image. or at the same time, actually, your body is slowly moving just a little bit. So once again, you're gathering little bits of information about the world around you from slightly different angles, and that's going to help you to process the image. There's even, more interesting sort of more subtle elements, like even the amount of muscle strain in your eye as it's sort of reshaping the lens. Your brain's actually able to tell, oh, how much strain is your eye under, which sort of helps you know where you're focusing. And so there's lots of different sensors going on in your brain involved in vision. Well, if we try to apply that into a traditional sort of computer vision application, you've really got just one camera, or in many cases, sitting taking pictures of an object. So it's a much more difficult problem, which could perhaps be enhanced by having lots of different sensors, or, as we're going to talk about today, just making sure that you're collecting and storing all of that data that you have from the camera and trying to use that to better train the computer vision algorithm so that you can solve harder vision problems. So, what types of other sensors can you have? Of course, you've got the camera itself. The camera might be mounted on a robot, and so you can take information about where the robot has placed the camera. You can take information about the size of the object that you're looking at, compare it versus what you think you're looking at, things like colors, the temperature of the environment, barcode information, stuff like that. So there's a lot of information that you may be gathering on the plant floor, which you can use and tie into your computer vision system. Or, to be honest, it doesn't have to be a computer vision system itself. You can take all this data and mine it for other purposes. So lots of opportunity around vision in the big data area. So let's talk about an application that we have done about a year ago with a big three supplier. I think their logos are properly masked in this image, but some of you might be able to guess who the big three supplier is as we step through this. But the problem was a final assembly inspection. So we've got vehicles coming down. At the very end of the line, we need to look for the badges on the back of a vehicle. So, if it's a 4x4 vehicle, you want to see the 4x4 badge. If it's a flex fuel vehicle, you want to see a flex fuel badge, things like that. So you're looking for things that should have been stuck on the outside of a car, very colloquial terms. Now, as a vision application, this is very difficult, because when you're looking at the outside of a vehicle, you have really, really shiny paint. And in fact, it acts like a mirror. Now, if you ask yourself, what color is a mirror? Well, I suppose you get technical and talk about the different color paints. But technically, when you have a mirror-like object, the color of the mirror is whatever is reflecting off of it. So if you have a mirror in a blue room, the mirror is going to look kind of blue. If you have the mirror in a brown room, it's going to look brown. If you have a light shining at the mirror, you're going to see a bright, shiny spot. You've got this problem of mirror-like surfaces that you want to try to inspect. Then you have a second problem that a lot of the badging that we put on our vehicles these days are themselves very shiny. So for example, a chrome badge. So you've got another shiny object. So what we're doing here really is looking for shiny objects sitting on top of other shiny objects. A very challenging vision problem. It's actually kind of funny when I think back a little ways. I remember in the, I think it was the mid-1980s or so, that my grandma drove this, frankly, hideously ugly kind of pea green Chevy Nova, I believe it was. And, it's sort of a nice matte surface and stuff like that. As I think back, I think, wow, it sure would have been nice if I could have done computer vision inspection on that car, because things would stick out beautifully on a hideous pea green background. But if you're trying to look for a shiny object sitting on top of another shiny object, that's going to be a big challenge. And then we had another twist where sometimes we were looking for that trim level where it was black badges on the outside of the vehicle instead of chrome badges, which black badges stuck out nicely if the vehicle was white, but it was the same shade of black as the black vehicles were. So sometimes we were looking for black objects sitting on a black object. So really big challenge from a vision perspective. a couple other things that were really thrown at us. We had limited control of the environment. So because of various health or various safety restrictions and stuff like that, we were not able to just put the vehicle in a fully shrouded environment. And so there's a lot of different ambient lighting around, or sometimes as the vehicle was going down the line, the vehicle behind it had its headlamps on, and so it was blasting additional light onto it, things like that. So we had a lot of environmental issues. So if we go back to the idea of, hey, this being a mirror that's reflecting whatever's around it, and we don't control what's around it, okay, it's going to be all sorts of crazy other things showing up in the mirror-like surface of our vehicle. Now we're going to make it even harder yet. This production line never stops. For this particular big three company here, this is one of their most profitable vehicles. They're running 24/7, almost 365 days per year. So there's never really a time where we can say, all right, just park a vehicle in front of this camera so that we can get things tuned in and stuff like that. So we had to sort of extract data whenever we could get the data. And then finally, a moderately high accuracy level for at least a computer vision system, 99.5% accuracy. You know, of course, from a Six Sigma perspective, 99.5% isn't all that great, though for many of you who have experience working with computer vision systems on your assembly lines, they often have a bad reputation of being even lower than that, even in the best of circumstances. So we were trying to tackle a pretty tough computer vision problem here. The basic solution that we had to do is we had to start gathering a lot of data so that we could train our computer vision algorithms to handle just the immense variety of different environments and circumstances and get our computer vision systems tuned in. So that's sort of the basic core problem we were trying to solve for the customer. And then there are other, lovely obstacles. So so three of my favorite here, one of which is trying to get the system to trigger when we're looking at the right part of the vehicle. This is a basic systems integration problem, but we sometimes have people walking around. They may, accidentally trigger the sensors early, and so we get a picture of, for example, the side of the vehicle instead of the back of the vehicle. Or I talked briefly about this, the image on the lower left side is a case where the vehicle behind it had its headlamps turned on, and so when you have a nice high-power image or light blasting against your vehicle while you're trying to inspect it, it's very hard to see the features that you're trying to pull apart. And then finally, my favorite one, the lower right-hand image, is the picture of a fine auto assembly worker's behind in our image. In theory, this is a spot on the assembly line where there should not have been any workers, and in fact, this created a certain amount of a stir because there is a pit underneath the vehicles, and it's a safety issue for them to be there, and we have cameras pointing at it, and in certain cases, we actually get pictures of the person standing right there, including their face or enough of what they're wearing to see. And we had some rather interesting discussions where sometimes the managers wanted us to give them lots of data so they can then go after their union workers and say, oh, you're having all these violations. And as you can imagine, we did not exactly want to get caught in the middle between a management union dispute, especially. So kind of some interesting challenges when you do have this image data. We kind of talked a little bit at the very beginning about how there's other features in some of these images that you may decide later that you want. One of them could be, here's a picture of a person who is somewhere that they're not supposed to be. And so kind of interesting challenges that you run into when you're working on a problem like this. But anyway, another important point here is that a lot of sort of pundits, when they talk about big data, they kind of dismiss the idea of data quality, kind of that sort of, oh, you got lots of data, so you don't need to worry about whether or not your data is any good. That is absolutely, absolutely not true. It may be applicable in certain contexts, like where the predictions that you're making have much smaller consequences. So I like to actually pick on Amazon a lot. The Amazon recommendation system. A lot of people will say, oh, look at what they're able to do with data and predict what sort of products that you might like to buy. Well, for one, I don't tend to find the predictions very accurate. But the other thing is that the cost of getting a prediction wrong through Amazon's website, if they tell you, no, you want to buy this particular CD or this, new watch or something like that, they get it wrong, I just don't buy, no big deal. But if you get something wrong in sort of a manufacturing context, you've got the costs of rework, or you may be releasing a defective part into the wild, and then there could be warranty claims, safety issues, things like that. So the consequence of getting things wrong is much higher. And so getting good data is extremely important. So if ever you read about people saying, it's big data, data quality doesn't matter, that's completely incorrect. That said, there are some tools you can use to help tune things, and we can even talk a little bit about how you can try to manage your data quality. So for us, what we actually had to do is start going through and what we call data labeling, which is we want to take this data and find, for one, bad images so that we could remove them from the data set so that those images were not used to train our vision algorithms. And then two, we actually had to be able to go in and say, hey, on this image there is a 4x4 badge, or on this image there is a flex fuel badge, so that we could then go through and automatically so that when the automatic training algorithms started to go through this, we had a training set for them. Now, there are a couple different ways that we can do this, and one way, of course, is the developer-labeled approach, where we create an interface so that our vision engineers would be able to go in and just very quickly identify what features are present or absent. One of the important things here was to try make it fast by having the computer vision algorithm first guess what it thinks is there, and then let the developer sort of correct it as necessary, and that really cut down on the time it took to train up the algorithm, rather than starting from the level of going through and manually identifying every single feature on the image. So we were able to set that up. It actually got to the point where you could label an image, every couple seconds or so, which allowed us to create fairly large databases of images to train the algorithms on. And it was important to get lots and lots of potential images because we have that high variability in the environment. So we used a lot of data in order to compensate for the uncontrolled environment. The other thing, though, which is kind of a nice thing emerging out of these more user-friendly data type of applications, is trying to enlist people, the end users, as a source of data as well. So, for example, if we have our system and it makes a call that says, this is a fail here because it's supposed to have a flex fuel badge on there, the user can actually then go in and say, nope, that is not correct, and correct it right in the system. And so for those of you who have any sort of background or have read about some of the consumer internet side of big data, you may be familiar with the idea of crowdsourcing, trying to get your users to do the work for you. This is kind of a plant floor version where we can show a dashboard to the operator, and if we make the call that says this is a failure, they can then go and say, no, it's not. And then we take that information back and use that to help automatically retune the algorithm. So we can label the data that way. It also helps us then to get rid of some of the bad data. So for example, if there's a picture of a person in the image or something like that, we would label that as an obstruction to the image, things like that. So strong emphasis on labeling and managing the data so we can get a nice big data set as quickly as possible. Then, of course, it doesn't do you any good if you've collected a lot of data, but you can't get access to the data. So, plant floor environment is not always the easiest environment for doing anything with networking. But we did our best to actually transmit the data all over. We started off with, if you look at the bottom of my graphics, we had sort of our cameras, which were taking pictures of the vehicle. And also we worked with the manufacturer's MES system, so they had to actually tell us, hey, this type of vehicle is coming down the line next, so that you know what to inspect and look for and make the pass-fail call. So at the lowest level we had those. That's a sort of traditional LAN type of network connected to our own little local cloud that we had there. And then at the local cloud, we did most of our local computer vision processing. But that was sort of assuming that we had well-tuned computer vision algorithms. So from there, we could actually take that data and push all the passes, all the fails, all the data that we had about the vehicles up to a private cloud, I should say. It was actually, out there through the internet to a private cloud where we could then use that data to retune the algorithms. We'll talk about that a little bit more. So we at Site Machine were then able to access that sort of data. But also we made it possible so that the quality managers could get in either at the local data or through the cloud to get their data. So it was kind of nice. The quality manager then, if he had to go to Europe or whatever to visit a plant there, he could still kind of keep track of what was going on back at home all through the connected systems here. So we had lots of connections all over the place, tying together cameras, the factory MES system, our local cloud, the public cloud, our computers, the quality managers' computers, all needed to be tied together. And some of it we were able to do via VPN. What's kind of funny is we started to notice a lot more applications where people just rely on cellular. So there are now actually a couple even device manufacturers who will have partnerships signed with, say, Verizon or AT&T, which will just automatically take their sensors, their cameras, whatever they're working with, and just tie it into the cellular network, basically recognizing that it can be difficult sometimes to get a good network drop brought right to the machine. So just get yourself a 3G connection. Now, of course, you may say 3G, don't you have 4G and all that sort of stuff? And the answer to that is basically in the sort of environment with all the machinery around, usually the connectivity is pretty weak. And so we find that we don't usually get a good 4G type of connection. It's usually much more degraded than that. But we do our best given the cellular technology is available. But it is sort of a big challenge when thinking about sort of big data applications on the plant floor. There's a growing plethora of sensors out there which can be network connected, but sometimes getting from the device to either a local cloud, or if you are a company that wants to do, say, public cloud or whatever, pushing that data the sort of last mile there is still a little bit of a challenge, and you have to be a little bit creative sometimes in order to get access to that data. Once we get that, though, we were able to get sort of an almost completely closed loop system for automatically retraining the vision. So what we would do, if we kind of start at the top of that circle-ish, diamond, whatever, we would scan vehicles and collect a bunch of data. From there, we would take that data and either using the operator corrections, if they said that our evaluation was incorrect, or using the developer label system, we would go through and mark up those images to make sure that we had a good training set. Then we would pass that over to the vision learning algorithms, and everything would get auto-retuned at that particular point. And I do say auto-retuned with, I should put, I don't know, air quotes around that or something like that. Once we actually did retune those algorithms, we didn't just automatically push that to the plant floor. We actually had to kick out reports, have sort of a human being look at some of the results, things like that. Because as you may recall a little bit earlier, I was talking about the cost of failure here. If you push a bad update to the system, suddenly our vision system would start malfunctioning and say either too many false passes or perhaps worse in terms of the perspective of the local engineers, too many false fails, and that could make people quite grumpy at us. And so although we auto-retuned the vision, it still went through sort of a human review process before it actually got deployed down to the plant floor. And then we can sort of complete that circle again. So you deployed that vision update, we scan more vehicles, we use those vehicle scans to get updated, better images, and lather, rinse, repeat, sort of type of system. Early on in the system, it was a matter where we had to literally do the cycle on a almost everyday basis as we were trying to get the vision algorithm tuned. over the course of a couple of weeks, though, got better and better and better, and actually now at this point we're in a almost steady state where it only requires periodic tweaks to get the system running at its best capacity. But I should actually point out here, this is actually a nice system as well for remote management, so that when things do start to go wrong, if there is a problem with the vision system, we can do a lot of the maintenance right from our own office, so we don't have to send somebody on a drive over to the plant in order to do system maintenance. We can correct a lot of things from the comfort of our own offices. So it's also kind of nice from a lazy engineer perspective too. So it's not quite 100% automated, but we are starting to get towards that holy grail, especially in the industrial internet, perspective of automatic, machine over to the analytics, back to the machine. We are starting to get closer to such an application. And as long as we were collecting this data originally primarily for our own internal purposes, we found that there were other applications for this data too. So as a vision developer, we would often think about, how do we test results from our vision algorithms and show, which errors are vision errors, whereas which cases did we actually have a true fail coming off the system. And we can then start diving into, vision failure rates. Maybe one badge was much more challenging than another one, so that we knew that we had to go through and focus on retuning that particular one. So it gave us a lot of insight in terms of how to take the next steps and get the best quality possible. Also, it was helpful so that we could communicate with our own management, and so when they're asking us, hey, how much longer is this project going to take? How are you guys doing? Can we invoice them yet? Things like that. We had some good data that we could use to say, oh, we're almost to our goal. Look at the sort of trend line here. We think it's going to take 2 more weeks of collecting data or something like that. So very helpful from the vision developers. But the other thing we found, as I briefly alluded to before, is the quality manager wanted to see this all as well. And so if you think from the quality manager's perspective, officially what they want to know is how often are they actually truly making a bad part. What we found, though, is actually a slight variant on that is what they really, really wanted, which was how many times do we incorrectly fail a part. So they wanted false fails. It was kind of an interesting quirk. We'll talk about this a little bit more in terms of the communications around this and what the information does to the system. But we were actually surprised as we started to dig into what metric is used to evaluate us, and we were a little bit surprised. I'll talk about that a little bit more in just a minute. And we also had some other issues. So I already talked about people in the camera. We had a lot of issues around that. And that was supposedly a safety violation, so the managers were kind of interested in that. Or a similar problem, we actually had some really blurry images, which was an indication of when somebody was actually driving a vehicle down the production line. It's supposed to be on a track, which is taking it itself, but you can also drive it. And there are some weird incentives around that. We actually found that from time to time, especially on weekend evenings, we found that sometimes they would be driving vehicles down the line as fast as possible, basically taking previously inspected vehicles, quick take it, drive it down the line so it would count towards their quota of vehicles that had to be inspected, and voila, they get done early. So you can kind of detect some weird things like that. So it is kind of fascinating that we started off with an application for is the 4x4 badge on your vehicle, and you get some of these other funky little side issues that popped up as well. So it was kind of an interesting learning project in terms of other uses of the data. But as I said before, one of the really interesting things was how are we actually being evaluated? So a lot of these sort of line inspectors were mostly interested in fails, and particularly false fails. Now, of course, the reason why they care the most about false fails is whenever we said, oh, this vehicle is, bad, but it wasn't, well, we just wasted a bunch of time because, we say it's a false fail. They actually then send it over to the shop to get rework done, and they look at it and say, what, this is just fine. What are you talking about? So it wastes a lot of people's time. So a lot of them are sort of, don't waste my time. You're annoying me when you give me a false fail. Don't give us false fails. Well, of course, one of the natural sort of responses is to say, well, you know what, there's always going to be some sort of defects. These systems are not perfect, so we'll just adjust the tuning here a little bit and, you know, potentially false pass more often in exchange for fewer false fails. Well, of course, that makes the inspectors happy, you know, most of the time until audit time comes along and suddenly we're false passing too many vehicles, and then they get even more mad at us because their manager is mad at them. And so there's this fascinating tension going around in terms of tuning the algorithms and trying to make sure that we are properly balancing false passes and false fails. So that was sort of an interesting thing. Another thing is, you know, they may not even be seeing the false passes, you know, other than audit time. So it's like, all right, let's build up a truth table, a full truth table, so they can see number of false passes, number of false fails. It's kind of nice to build these because actually the average person can really, you know, understand that. It's a nice 2x2 sort of grid application here. It's computationally very simple, no fancy statistics or anything like that. The fundamental problem with building something like that is that would actually require us to re-inspect every single image that our algorithm did. And we don't necessarily want to get involved in doing something like that. You know, why on earth would we have our engineers manually inspecting every image when we already created an automatic system to do that? So it kind of defeats the purpose. So we would periodically run a sort of full analysis just to get a complete picture, but this was not by any stretch of the imagination something we did all the time. Or, you know, we can go to a much more sort of statistically driven accuracy reporting. This was sort of fun to really get into. And if you think about how you report this accuracy, you know, we said we want to hit 99.5% accuracy. Well, if we say that we're 99.5% accurate, is that actually a good computer vision system? We might say, well, of course, this is an excellent computer vision system because many computer vision systems have much lower accuracy than that. The alternative, though, is to understand what is the accuracy of the underlying process. So if the actual production process gets things right 99.9% of the time, you know, we could actually create a very, very naive algorithm which just always says pass, and then our system would also be right 99.9% of the time, and then would be wrong. But of course it would be wrong, you know, only for that 0.1% of the time. And so, hey, we look great, don't we? Of course, that's a little bit ridiculous. It doesn't do any good. Why on earth would you pay for a system that, you know, only does that? So if you kind of get into, you know, even this is, I'll call it basic statistics, maybe intermediate statistics, you know, sort of like the AIAG recommends using Cohen's kappa for this, but it's basically trying to control for the fact that randomly you're going to be right a lot of the time. So what we want to do when we assess our accuracy is we want to figure out how much better than a random system are we. And, you know, the statisticians in the crowd could, you know, go into all sorts of debates about whether or not Cohen's kappa is itself a good metric. We aren't necessarily going to go there here today, but the sort of important part here is that, you know, there are better metrics, but at the same time as you say something like Cohen's kappa, suddenly everybody's, ooh, that sounds fancy pants, you know, I'm not a statistician, I'm not going to be able to understand this, and there's a certain then pushback sort of, okay, this is no good. So we kind of lose some of the average user accessibility of the system. So there's a lot of interesting effort to sort of triangulate between good statistics and accurate reporting of what we're doing. What we actually found was, for the most part, for the average Joe user, even if we just tried to show tables of numbers, like we kind of showed on the left-hand side there, even that can be just a touch intimidating. But one huge benefit of a computer vision system is people understand pictures quite well. And so the final sort of accuracy report that we started providing, we gave them the table of numbers, but also actually showed pictures of every single failure. And the sort of neat thing about that was then the quality manager was able to take those reports, print them off. Unfortunately, they had to print it, but you know, whatever. Print them off, and they could, at their team meetings, just go through and say, hey, look at this. Here are your defects. Here's an actual picture. And the sort of visual power of that was quite interesting. It's an excellent tool. So beyond just pulling out sort of numbers as data analysis, images are a great tool because we naturally sort of psychologically respond to images in a way that most people don't respond to a table full of numbers or even charts or things like that. So it's kind of a nice approach. So maybe to kind of tie things all together, a couple of the major things that we learned, that data isn't just for reports. You don't just pull a bunch of data together and slip it into a bunch of pie charts or something like that. We were actually able to use our big data application to automatically retrain a computer vision system. So we could get close to the sort of holy grail of the machine doing its work, analytics on the results of that work, retrain the machine. There was actually a little person sitting between the analytics and the machine there, so we aren't quite to 100% automation, but we're starting to get there. We did have moderate problems with data quality. We had the problem, of headlights on right behind the vehicle. We had problems with people's butts in the way of our camera, things like that. So we really had to think about data quality as a problem. So we really had to focus on multiple ways that we get feedback on data quality, both internally for our engineers to be able to quickly manage the data quality problems, and also trying to find ways to get the operators to think about how they can sort of flag problems in the data as well. And then, this is not just about, production defects. We were able to use the data for many different things around the system configuration, environmental drift, so we could retune our algorithms, things like that. So lots of good applications there coming out of the fact that we were able to take the rich data source of images, mine that, apply that, and close the loop for a system. Future steps where we're going right now, we're actually now starting to be able to then pull together data from multiple different sources, put them into a convenient dashboard, look for trends in that. Are you going up or down? It's also actually kind of helpful. Sometimes these systems do break, and so suddenly if you start seeing a flat line on a major dashboard, you can say, uh-oh, there's a problem, and sometimes we can actually even respond to those problems before the local plant knows that there is an issue. So as we're pulling things together into a combined dashboard, there's a lot more opportunities to make sure systems are up and performing as they are expected to. But the fundamental lesson here is don't throw away your data. You've got all these sensors out there. You've got computer vision systems collecting lots of data. There's lots of different opportunities to go through that data, mine it, find some good insights, and improve your processes. And that's sort of what I had planned here. And I guess at this point we'll open the webinar up for discussion.
Well, that was an excellent presentation, Kurt. Thank you so much.
Thank you.
Well, I'll say this. We don't have any questions so far, so that must mean that you did a really excellent job. But
all right. Well,
we'll give a few minutes.
Nice weather. Cool.
Okay, somebody is asking, can this be used for automated medical devices?
So yes and no. It's actually kind of funny because my wife is a nurse, and so it's fascinating to talk to her about the state of all information technology in medicine. A lot of the newer devices, it is getting a lot easier to plug in, pull in the data, do automatic inspection, things like, or to aggregate the data, do analysis on the data. So it's getting there. There's a lot of older devices which simply predate the desire to actually connect two devices together, and so it's extremely difficult to get the data off of it. So it kind of depends on how old the hardware is. We do have a lot of experience trying to connect different devices, and you can kind of get through it, but it really depends on the age of the equipment that you're dealing with. That said, if it's also a specific vision application, it also depends on what type of vision analysis that you're doing. I know that actually the core part of our vision software is open source, and so there are people at Harvard Medical School who are even using that to do automatic inspection I shouldn't call it automatic inspection, automatic analysis of imaging, medical imaging. but I don't keep in touch quite as much with the medical side and how they do stuff.
Okay. Thank you. We just have a comment here. Someone saying Continua Health Alliance puts together standards for medical interoperability. It's more just a comment.
Yeah, no, that sounds right. I'm quite confident that this has been an identified problem, and so I'm sure there are folks out there doing good work to make it easier to tie these systems together in the medical field.
Yes, that makes sense. I think it's can be used for across broad applications in any field. So health just happens to be a big one.
Exactly. Lots of money in health, and it's been a major government push to get it done too. So.
Yes. Let's see. Okay, somebody else is asking, what system do you recommend to store data and also to work with big data? It's kind of a general question, I suppose.
Yeah, so a lot of that starts to get down to exactly what the application is and who needs to access it. So there's not really a one-size-fits-all technology. I mean, I'm sure that our marketing guys would say, hire Site Machine and we'll tell you, but I'll also give you the high-level overview, which is different technologies have a lot of different strengths. So, for example, these days, everybody's sort of, oh, you got to have your data lake plus Hadoop or something like that. When you actually get down to the technology, Hadoop as a specific technology really refers to a much larger ecosystem. It seems that Spark is actually starting to be the more popular system over Hadoop there, so that's very popular if you have really, really, really big data types of applications. But to bear in mind there, one of the biggest limitations with those sort of the Spark Hadoop ecosystem is it's still batch processing. You can do what's called micro batches, which allows you to work with smaller but faster feeds of data, but that still is much more batch processing oriented. We do some work with Storm actually for the real-time data feeds, so we like that. Mongo database, MongoDB, is terrible if you're doing data aggregation, but if you're just doing a sort of raw data store where you have a lot of data that you need to dump somewhere and that you're going to be looking up by sort of individual keys, it's not a bad technology. And to be honest, some of the, I'll call it slightly older database technologies do okay for what I'll call medium data applications. So Postgres or something like that is a perfectly good SQL application. Folks like Oracle would love to charge you a very large price tag to host on one of their systems. But one of the biggest challenges is that, 3 or 4 years ago, I would have just said, oh, Hadoop, because that's what was out there. Fortunately, though, in the last couple of years, there's been a much more nuanced I shouldn't say nuanced, basically lots of different companies have come in and said, hey, Hadoop is not a one-size-fits-all solution. Here are the other technologies which, are going to help you depending on your specific application. And so there's better technologies to serve everyone's needs, but it does make it harder to provide a webinar answer that just says use technology X.
Thank you. I think that was a pretty comprehensive explanation.
Mm-hmm.
Let's see. Oh, we're just getting several people are just saying thank you very much. The presentation was great.
Cool. Thank you.
Somebody is asking, is it possible to use this in a clean room equivalent to an OR that makes, I guess, medical drugs?
Yes, we actually do have a guy on our staff who comes out of Amgen, and I know I've been at one of his little talks where he's talked about doing these types of applications in these super duper clean rooms, the clean rooms of the clean rooms. I will be perfectly honest that I am not the guy who can answer that question in a competent fashion because that's not my background. But if you would like, send me an email and I'd be more than happy to put you in touch with Ryan, and he can talk about that sort of stuff in great detail.
Thank you. Okay. All right. Well, okay, here's somebody else is saying, do you think this would have an application in service industry?
Yes and no. That has been sort of one of the holy grails. It is actually kind of funny that computer vision in particular, a lot of the money is going into monitoring people, which is slightly scary what they can do. But what gets a little bit more interesting is, what does it actually mean to do big data generically in the service industry? And then what are your sensors in that particular case? What type of data do you collect? There is, of course, a lot of work about big data in terms of sort of the marketing and sales side, trying to understand consumer behavior. But if you are trying to then monitor your internal processes, I think that's a little bit trickier, mostly because it's not quite as automated. Manufacturing plants are actually wonderful for big data applications because you got sensors on machines all over the place, and so really the only problem is connecting it and dealing with the fire hose of data. In service industries, it's I'm not going to say impossible, but it's a lot trickier because you don't have that same prevalence of sensors everywhere in order to start tapping into. And so the short answer is, I guess, yes, but it's harder.
Okay, thank you very much. And I don't see any more questions coming in at this time. All right, so at this time, I want to thank everybody for attending today. A recording of the webinar will be available within the next few days on the Statistics Division's YouTube channel, which you can locate at youtube.com/ASQStatsDivision. So be sure to share this very informative webinar and our other archived webinars with your friends, coworkers, colleagues, and anybody who you think would be interested. Also, we do encourage you to check out the division's LinkedIn page as well as our events calendar. The events calendar can be found at asq.org/statistics, and there you will find all the latest news on webinars, conferences, and many other topics. Also, Kurt has very generously provided us with a PDF version of his slides, which I will send to all attendees within the next day or so. So, Kurt, thank you again for taking the time to present with us today. I know we all learned a lot, and I thank all the attendees for your time today. So,
Thank you very much.
Well, thank you.